Nevada desert, some of the most desolate acres to be found anywhere in the United States. Home of the Nevada test site, continental locale of the Atomic Energy Commission's nuclear testing program. Here, on some 600 square miles of desert waste, the United States tests laboratory-designed nuclear devices. These tests have helped the nation maintain its military strength. They have made important contributions toward the development of weapons needed for defense. But aside from weapons development, these tests serve other vital purposes. Since the United States has no nuclear monopoly, it must be prepared to weather atomic attack. Accordingly, structures of all kinds, shapes old and new, varied materials, are subjected to the withering effects of atomic explosion. From such tests and hundreds of other experiments comes knowledge that will help the nation's citizens withstand possible enemy attack. To house, feed, and provide the many other services needed by test personnel, a small city has been built on the edge of the test site, a city of dormitories, hutments, quonsets, and warehouses, a city called Mercury. And it is at Mercury that the Atomic Energy Commission's Civil Effects Test Group has its headquarters. Here, personnel of the Atomic Energy Commission and the Federal Civil Defense Administration work to obtain data on the civil effects of nuclear explosion. Countless questions are raised and the answers sought. How will homes, factories, and public utilities stand up under atomic blast? How will survivors of devastated cities be relocated? And perhaps most important of all, how will the hazard of radiation from fallout affect everyone's chances for survival? The answers are sometimes found only in the presence of an actual nuclear explosion. As a result, specialists are brought to the Nevada test site to gain experience under more realistic circumstances. For nowhere else in the United States does fallout occur in quantities and under conditions that might be related to fallout from weapons in a nuclear war. These men journey to Mercury to learn more about fallout, to assess its hazards, and to develop ways to cope with it. Already highly trained in radiological defense, these specialists bring with them the necessary skills and equipment to evaluate fallout, whether in dangerous concentrations or not. Others flying aircraft touch down on Mercury airstrip to help usher in a new and faster means of assaying fallout fields. They hope to develop further a way by which pilots flying light aircraft can quickly and accurately survey large areas for radiation levels. And they too are well equipped to do their job. Before coming to Mercury, these pilots of the Civil Air Patrol underwent rigorous training courses in their home communities under FCDA auspices. In fact, they were picked to come to the test site only after they demonstrated proficiency in radiological defense measures. But in spite of their abilities and qualifications, these men start again at Mercury. From the ground up, the awe-inspiring phenomenology of atomic explosion is resurveyed.
As you can see, we've got a lot of work to cover in a very short period of time. So, with this introduction, let's get on with the show. First of all, we intend to discuss some of the basic data on bomb phenomenology. All of you are familiar with a so-called nominal type bomb. We actually base many of our civil effects projections on what we know this bomb did. Some of the shots here at the site are close in yield to that of the nominal bomb. None, however, even approach the megaton yields of our thermonuclear devices. However, apart from magnitude, the principal effects of a nuclear detonation are the same: blast, heat, and radiation. Our chief interest, of course, is in the radiation effect. But before we take up the subject of radiation from the standpoint of nuclear explosion, let's take a look at radiation in general. Marlowe, if you're ready, let's roll the film. First of all, gentlemen, man didn't start radiation with the atomic bomb. It's been with us a long time. In fact, ever since the world began. The very crust of the earth on which we live contains radioactive elements. No matter where we live, we are exposed to radiation from the earth. On the average, each of us receives yearly about 40 milliroentgens from thorium, about the same amount from potassium, and about 20 milliroentgens from radium and uranium. In addition to this, we get about 30 MR per year from radioactive potassium and other radioactive elements present in the body. Man is also exposed to radiation from outer space in the form of cosmic rays. At sea level, we each get about 35 milliroentgens a year from this source. If we're inclined toward mountain climbing as a form of exercise, we're apt to get even more. For the higher we go on this earth, the more radiation we get from cosmic rays. For example, at 5,000 feet above sea level, we pick up about 65 milliroentgens a year, 30 or more than at sea level. Even in our quest for better health, we expose ourselves to radiation. Since the discovery of X-rays, man has increased his radiation exposure many hundreds of times over that which he receives from natural sources. A routine chest X-ray, for instance, may give from 1/10 to 1 Roentgen per exposure, while a fluoroscopic examination runs from 10 to 20 R per minute over the area exposed, depending upon the technique and equipment used. Now, what is the situation relative to radiation from a nuclear explosion? The fact is, whenever atomic energy is released, whether by fission or fusion, there are released with it certain powerful radiations. These radiations are caused by the transmutation, or if you will, the eruption or explosion of the atoms. To sum it up very briefly, we have to contend with two types of radiation whenever an atomic device is detonated. The first, initial radiation, concerns the release of neutrons and gamma rays at the instant of explosion. From a practical standpoint, this immediate radiation does not present a serious problem beyond the area devastated by blast and heat. The second type of radiation, and by far the more important from the civil defense viewpoint, is residual. This residual radiation comes from three sources: the fission products, or bomb ashes, the neutron-induced activity in the materials near ground zero, and lastly, from the unfissioned or unreacted materials in the device itself. This residual radiation constitutes our primary concern in radiological defense. It is the fallout problem. All atomic detonations produce fallout, but the nature and extent of it depends upon the conditions under which a bomb or device is fired. In an airburst, the fission products produced are very fine in nature, almost like an aerosol. Since they have only the dust and moisture in the air on which to condense, they tend to remain aloft for long periods of time and to fall out slowly. But in a surface or near-surface burst in which the fireball touches the ground, huge quantities of earth
and other materials are drawn up behind the rising fireball into the cloud. The radioactive atoms produced by the explosion adhere to these particles. Since much of this material is heavy, it descends while still highly radioactive. The deposition of this radioactive debris constitutes the fallout danger. Fallout can be divided into three categories: close in, intermediate, and delayed. The first, close-in fallout, is our main concern. This close-in fallout will occur within a few hundred miles of the burst and is usually on the ground within 10 to 20 hours. Furthermore, in a surface explosion, about 70 to 80% of all the fission products produced descend in the form of close-in fallout. The second, intermediate fallout, tends to descend very slowly. Although gravitational settling has some effect on this downward diffusion of radioactive debris, the primary cause for removal of such debris is precipitation. This intermediate fallout usually occurs within a few weeks after the detonation. The third class of fallout, delayed, is the result of the extreme heights reached by the debris from thermonuclear explosions. We actually know very little about the behavior of this high-altitude debris. Eventually, of course, it too descends, but this may take months or even years, and by this time, decay has lessened the hazard. We also know that stratospheric storage of radioactive debris serves to disperse it, thus minimizing the chances of locally high concentrations. For all intents and purposes, then, delayed fallout is of much less concern to us than close-in fallout, that which occurs within the first 10 to 20 hours. To outline the areas of this fallout, to report the varied intensities of its field, and to evaluate the hazards is our job. Since an enemy attack with nuclear weapons will almost certainly result in the contamination of large areas, the survival of persons within these areas will depend upon us. As members of the radiological defense team, whether as monitors or radiological defense officers, it is our job to detect, measure, analyze, and make accurate judgments as to the hazards involved in a given fallout field. To carry out that responsibility, we have to take precautions ourselves. A rad defense worker is of little use in an emergency if he's allowed himself to receive exposures in excess of the maximum permissible levels. Part of the equipment you'll use here are these personal dosimeters. The first is the CDV-138. This is an ion chamber instrument, as are the other two I'll show you in just a moment. It has a range of from 0 to 200 milliroentgens. Because of this comparatively low range, it can be used most effectively for training purposes. The operating principle of the CDV-138, stated simply, is this. It is first charged to 160 volts. This charge causes a quartz fiber to be repelled from a metal plate. When exposed to radiation, the air in the chamber surrounding the fiber is ionized and ion pairs are formed. This decreases the charge and allows the fiber to again approach the plate. By holding the dosimeter up to the light, the fiber can be seen in relation to the scale. The position of the fiber on the scale corresponds to the amount of radiation to which the instrument has been exposed. The operation of this type of dosimeter is like that of a voltmeter, the decreased voltage being converted and indicated as an increase in the absorbed radiation. These other two dosimeters are the same in operating principle. They each have, however, an added condenser which allows a greater initial charge. Hence, more radiation is needed to reduce that charge. The CDV 730 has a range of from 0 to 20 Roentgens, while the CDV 740 registers from 0 to 100 R. The final type of dosimeter we'll use here at the site is the film badge given to you upon your arrival. The test site Rad Safe organization requires everyone to wear it. Inside the wrapper are two pieces of film, one low range, one high range. Between the two, they will register from 25 milliroentgens to 100 R. The lead shield cuts out beta and low energy gammas. Gamma rays passing through the lead shield are powerful enough to penetrate 5 centimeters into the body, thus constituting a personnel hazard. The survey meters you'll use here are all multi-range instruments. The CDV 700 is a portable survey meter utilizing a Geiger tube as a detector. It is sensitive to both beta and gamma radiation, but its beta sensitivity is restricted to the moderate and high energy levels. The Geiger tube is encased in a shield. It is gas-filled and detects radiation through the ionization of that gas. With the shield open, it is sensitive to both beta and gamma radiation. By closing the shield on the probe, the instrument becomes sensitive to gammas only. 3 ranges of operation are provided. The ×1 scale requires 500 pulses per minute for full-scale operation. The ×10 scale, 5,000 pulses, and the ×100 scale, 50,000 pulses per minute. In terms of milliroentgens, these readings correspond to 5/10 MR per hour, 5 MR per hour, and 50 MR per hour of radium equivalent radiation. On the side of the instrument, just beneath the nameplate, a beta source is provided for checking the operating capability of the instrument. Because of its low range, the V700 is essentially a training instrument. In addition, however, it is useful in personnel and vehicle monitoring. Inside the casing, if you'll give me just a moment to remove the instrument, you'll find the circuit box, which comprises the batteries, the high voltage supply, the pulse shaping and metering circuit, and the calibration screw. The other instrument we'll use is the CDV 710. This is a gamma measuring air ionization instrument with ranges of from 0 to 5/10 R, 0 to 5 R, and 0 to 50 R per hour. The range selector switch also serves to indicate the 0 and circuit check positions. This particular instrument is zeroed by turning the control until the needle indicates 0 on the dial. Inside, the 710 is much like the 700, with the addition, of course, of the ionization chamber. This chamber is hermetically sealed to minimize the effects of temperature and to eliminate altitude and moisture factors. The 710 will be the workhorse in any attack situation. The other instrument we have here today is the CDV 720. And although we won't be using it in our exercises, it might be well to say a few words about it. It, too, is an ionization chamber instrument, but unlike the 710, can measure beta radiation. The beta shield is located on the bottom of the instrument, and when opened, exposes the beta window in the chamber. The 720 is a high-range instrument and can measure up to 500 R per hour. Now, if you will, gentlemen, and before we break for lunch, please check out your survey meters and your dosimeters. At 1300 today, we'll meet back here for transportation to the calibration ranges. Those of you with the 700s will go to the range near the decontamination building. The rest, those with the 710s, will go to the 200 Curie source just beyond the forward area checkpoint. I think that's all for now, gentlemen. Thank you very much for your attention.
Since the survey meter is the sole means by which the monitor may detect and measure the varied intensities in a fallout field, accurate functioning of the instrument is of vital importance. Operating as two-man survey teams, the monitors calibrate their meters according to well-defined procedures. After waiting 30 seconds for the circuitry to stabilize, operability of the instrument is checked by opening the beta shield and placing the probe next to the beta source. When the instrument is operating properly, the indicator should fall between 1.5 milliroentgens per hour and 2.5 milliroentgens per hour. If the indicator falls above or below this range, the instrument is removed from the case and the calibration screw adjusted. Rotating the screw clockwise increases the reading, while counterclockwise rotation decreases it. When the instrument is reading properly, it is returned to its case and the beta shield is closed. If the instrument does not respond to this procedure, it will not calibrate properly and should be repaired. The completion of these steps by all monitors is the signal for a known intensity source to be placed on the range. Here, a relatively small 30 millicurie cobalt-60 source is being employed. Extending from the source stand are 7 wooden legs. Measured distances from 1 to 20 yards are marked on these legs, taking into consideration the known strength of the source. The monitors select one of these points at which the dose rate in milliroentgens per hour has been calculated. With the probe held carefully over the mark, the intensity reading is noted and recorded. Using this source at 5 yards, the V700 should indicate 1.9 milliroentgens per hour. If it does not, the scale reading is again corrected by rotation of the calibration screw. The monitors then take readings at all points on the range. At each subsequent point, the reading is noted and logged. No further adjustment of the calibration screw is made, since the results for each instrument will be graphed and maintained as the meter's characteristics. Calibration of the V710 and higher range instruments is accomplished in much the same manner as with the V700, but warning signs and massive concrete shielding indicate the use of a source of much greater intensity. Beyond this shielding, radiation from the 200 Curie source in use here is so intense that it is necessary for calibration to be effected through the use of a telescope. Time and care are necessary ingredients of this operation. Before the monitor can make an adjustment or move the meter, the source must be lowered into a 4,000-pound lead pig beneath the platform. Once the accuracy of the meters has been determined through calibration, the monitors begin field exercises designed to give them practical experience in field survey techniques and procedures. Before moving into a fallout field, the monitors are briefed by the squad leader. Final reviews of communication and record-keeping procedures are held. Grid maps of fallout areas are studied. Then the monitors draw their equipment and move out for field exercises. The ground monitors are organized as field survey squads, with each squad employing a mobile trailer equipped with survey meters, handy-talkies, and higher power transmitters for base communications. In the field, the monitors in 2- or 3-man survey teams will radio their readings to the squad leader and assistants back at the trailer for relay to the radiological control center. Meanwhile, pilots of the aerial survey units ready their aircraft and instruments for their part in the exercise. While here, these airborne monitors will develop altitude correlation factors for the V710 instrument and continue their study of aerial monitoring techniques. Inside the aircraft, 3 V710s are installed, with each meter set on a different range to eliminate the need for scale switching. 2 aircraft will be used by the group, with one flying crisscross broad survey flights and the other flying detailed patterns over markers drawn on the desert floor with line. The main legs of these markers are existing roads and are 1 mile long with cross lines every 1/10 mile. Several of these will be laid out so that at least one will be in the path of fallout from a test device. In flight, the aircraft will fly the full length of the primary leg of the pattern, then bank right and fly the secondary leg. It will then turn right and retrace its path over both legs. In this manner, each point in the pattern will be passed over from both directions. The flight survey crew is composed of pilot, location spotter, and reader. When the plane enters the pattern, the spotter leans into position. As the aircraft passes the 10th mile crosses, he signals the reader, who notes and logs the meter readings. Meanwhile, at the Radiological Control Center, methods and procedures for the upcoming exercises are being evolved and perfected. As messages from units in the field are received and recorded by trained radio specialists, they are relayed to the staff, which is responsible for maintaining accurate records on the number and locations of units in the field. In addition, the staff will keep up-to-date records of the accumulated doses of all survey crews. Copies of incoming messages then go to the plotters. On the basis of this field radiation data, as posted by the plotters on maps of the area, the RADEF chief is able to determine the boundaries of the fallout field. In addition to the ground and aerial units, resources of the combined group include a mobile laboratory. Despite the care and attention to detail taken to ensure the accuracy of field survey instruments, certain vital information can only be determined through more precise measurements. The mobile laboratory unit is equipped to perform this service. By preparing and measuring samples brought in by the monitors, highly trained laboratory technicians can provide accurate information based on the actual type of contamination. Thus, significant departures from normal decay rates can be determined. This is important since isotopes other than normal fission products may be deposited as fallout. In such a situation, stay time limits based on typical fallout would become useless or would require modification. Hence, samples of soil from fallout fields are given top laboratory priority. While the training units are developing and shaping their techniques and procedures, activity leading up to the shot itself is underway. Throughout the week preceding a detonation, a vast system of instruments is made ready to record necessary effects data. The instruments range from inexpensive film badges and thermal gauges to complex and costly neutron detectors. Many of the instruments are close to ground zero and are damaged or destroyed almost at the instant of detonation. But before they are destroyed, they transmit their all-important data. Nerve center of every operation at the test site is the control point at Yucca Pass, overlooking both Frenchman and Yucca Flats. From it radiate the myriad communication lines required to control such a complex operation. Into and out of it flows information from all over the world, as well as from other areas of the test site itself. The instrument panel in the control room reflects these intricate operations. Control of experiments is provided by a sequence timer located here. This device transmits signals which activate electronic systems, secure blast-proof doors, start ultra-fast cameras, and in some cases, arm and fire the device itself. These and hundreds of other details must be taken care of in proper order and at precise times if the necessary data is to be obtained. As H hour approaches, night weather briefings by test site meteorologists are conducted for unit project officers.
Gentlemen, that seems to be the picture as of the moment. With regard to your operation, prospects for fallout within the Nevada test site and the adjacent bombing and gunnery range are good. The winds, as they are now, will result in very little off-site fallout. If the winds maintain their present direction, and this, I'm sure, will make you flyboys happy, the fallout should pass directly over station marker number 2. Any questions? Okay. Good night. Happy fallout, honey.
Everyone has waited for this moment. Now, an actual situation is in the making. A situation that, barring enemy attack, cannot be duplicated anywhere in the United States. Everything that has gone before, the careful planning, development of techniques, and review of procedures, has led to this. All along the line, the units begin to function. The RADF chief and operations officer reevaluate their fallout prediction based on the latest weather information. Communications are established between the radiological control center and the operating units in the field. Every man, every unit, in proper position. Then, the long wait before the final minute is counted off.
-1 minute. Put on goggles or turn away. Do not remove goggles or face burst until fireball dissipates. Seconds to 0 time. 25 seconds. 20 seconds. 15 seconds. 10, 9, 8, 7, 6, 5, forward, 3, 2, 1.
Brilliance of the sun, the awesome sound and fury of the atoms split apart. This is nuclear explosion. above the desert, the atomic cloud hangs until wind begins to scatter it. Already, tiny radioactive fission products adhering to debris are starting to fall. Within the hour, the largest will reach the ground. Later, when on-site fallout has occurred, monitors of the permanent rad-safe unit penetrate the shot area. Once the fallout field has been surveyed and the level of radioactivity certified as being within permissible limits, the test groups may begin their exercises. Taking off from Mercury airstrip, the two aerial survey planes head for the shot area. One will fly the marker pattern, the other will crisscross the fallout field. Approaching the marker, the pattern aircraft descends to 1,000 feet for the first run. Tricky, this desert flying. Thermal updrafts and swirling eddies complicate the pilot's job of maintaining altitude and course. The crew seeks to establish altitude correlation factors for the V710 instrument. What is the dose rate at 1,000 feet, and how does it compare with the reading on the ground? Since the aircraft passes identification points at 70 knots, allowance must be made for the meter's time lag factor. What corrections, then, need be made for this ballistic effect? What is the shielding or attenuation factor of the aircraft itself? The answers to these and other questions are found only by flying an exact pattern and by making precise readings. Down the plane drops to 800 feet. The pattern is repeated. And so it goes until the last run, a mere 200 feet above the desert floor. To correlate the readings thus obtained with ones taken from a stationary position, a helicopter is used. As soon as the last pattern is completed, the whirlybird moves in to repeat the process. But this time, because of the copter's ability to hover, the ballistic effect of the meter is overcome. At each altitude and over each 10th mile marker, readings are taken right down to the desert floor. Meanwhile, the second aircraft is completing its mission. Using roads and other topographical marks, it crisscrossed the fallout area to determine its boundaries and intensities. These readings will be compared with those taken by the ground survey groups. Fanning out from their trailer headquarters, the ground monitors rapidly cover the area. To minimize personal exposure and to gather the needed information as quickly as possible, the crews move in with jeeps. Readings are taken at each milepost and other predetermined landmarks. The monitor quickly moves into the desert for several yards to eliminate any shielding effect of the vehicle. All 4 major compass points are faced to obtain an accurate reading. These monitors wear coverall-type clothing provided by the permanent rad-safe unit. The clothing aids in personnel decontamination when necessary by minimizing body contact with radioactive dust. As the driver heads for the next location, the reader logs his findings. Position, time, and intensity are carefully noted. At subsequent stops, the steps are repeated. While the monitor is taking his reading, the driver radios information from the previous stop to the squad leader at the mobile trailer. At the trailer, the reported reading is recorded, then the written record passed on to the squad leader, who transfers the location, intensity levels, and time to grid maps of the area. This information is then relayed via base radio to the control center, where reports from all units are flowing in. Here again, the message is recorded and the written record passed on to the staff, where it is logged. After posting on the resources map, the field information is sent on to the plot staff. Grid maps, identical with those at the trailers, are used to plot the fallout. Once the information has been plotted, it is passed on to the operations officer and the RADEF chief. On these two men rests the responsibility for drawing the fallout picture. In an actual attack situation, the lives of many people might depend on their ability to accurately plot and evaluate the fallout. Gradually, the limits and intensities of the field are established. Slowly at first, then rapidly as more of the units report. Finally, the fallout picture is complete. Properly evaluated by trained radiological defense officers, these multicolored ISO intensity lines mean more than 10,000 words. They might mean the difference between life and death in an attack situation. Not here in Nevada, of course, because every precaution is taken to ensure that off-site fallout is minimal. But in the event of enemy attack, in towns and cities, in villages and hamlets, on farms, anywhere and everywhere in our nation, services established to minimize the effects of nuclear attack could function effectively only by having accurate information on the boundaries and intensities of fallout fields. Police and fire departments, medical and welfare services, all would rely on the judgment of the radiological defense staff as the constantly changing pattern of radiation hazard is drawn. And so, men come to Nevada to work and plan for the day that all hope never comes. But until the international trust is firmly secured, still others will come to train for civil defense.